Good morning to everybody. You are going to study about microprocessors today. In this session, we are going to cover the objectives. What is a microprocessor, block diagram of a traditional computer and that of a microcomputer, classification of microprocessors based on word length, functions of a microprocessor in a microcomputer, bus structure of 8085 microprocessor, functions of various resistors of 8085 microprocessor, pin diagram and function of each pin of 8085 microprocessor, then generation of control signals IO bar, M bar, read bar, write bar. Using these three control signals, how to generate 4 control signals, then architecture of 8085 and its operation. So what is a microprocessor? Microprocessor is a programmable integrated circuit that can perform arithmetic and logical operations as well as which has decision making capability. So it can be embedded into a large system for controlling of the processing. It is nothing but CPU of a computer. Now let us see the classification of microprocessors based on word length. What is meant by word length? Word length is nothing but number of data bits that a processor can process at a time. Initially 4-bit processors were so initially in 1970s Intel introduced 4-bit processor which is 4004 used in calculators. Later 8-bit processors were introduced. One is Zilog's Z80, then Intel 8008, 8085, Motorola 6800. So these are generally used in control applications. One example is the single board computer such as STK85, which is generally we use in our microprocessor laboratories for study purpose. Then advanced processors are 16-bit processors. So these processors can process 16-bit data at a time. Intel 8086, 80286 or some of the 16-bit processors, they are used in computers. The more advanced processors are 32-bit processors and 64-bit processors. Pentium 2, Pentium 3, Pentium 4 or 32-bit processors which are using in sophisticated computers. Now let us see the block diagram of a traditional computer and its function. A traditional computer consisting of arithmetic logic unit, a control unit, input device, output device, memory. The arithmetic logic unit and control unit combinedly known as central processing unit. This central processing unit can take data from the input device and it can give data or can write the data into output device, and it can also access memory in both directions, that is it can read memory or it can write memory. When we go for microcomputer, the central processing unit which consists of arithmetic logic unit and control unit is replaced by a single chip which is nothing but a microprocessor. Let us see the block diagram of a microcomputer. Microcomputer consists of a microprocessor which acts as a central processing unit, an input device and output device, memory similar to that of a traditional computer. The only difference here is the central processing unit is nothing but a single integrated chip, that is a microprocessor. So here this microprocessor can take data from the input device or can give data to the output device, or it can access memory for reading or for writing. So that is the difference between a microprocessor computer and that of a traditional computer that lies with the presence of microprocessor. Now let us see what are the functions of a microprocessor in a microcomputer. The functions of a microprocessor in a microcomputer can be stated like this. So initially program is going to be entered into the memory of microcomputer with the help of an input device such as keyboard. So once the program has been entered, then the processor reads one instruction at a time. Then it matches the instruction with its instruction set which is available internally. When both the instructions are matched, then the actual data manipulation takes place according to the opcode which it indicates. So after the completion of data processing, the result can either be stored in memory or it can be sent to any output device such as LED or CRT screen. So not only these things, the processor can also respond to some external signals such as interrupt, reset, wait, etc., which we can study later. The overall functions so far we have seen can be classified into three categories. So there are microprocessor initiated operations, internal data operations, and peripheral or externally initiated operations. Now we can see these operations one by one in detail. Let us see microprocessor initiated operations. These operations are nothing but memory read, memory write, input output read, that is reading from input device, or input output write into output device. So these are the four machine operations that the processor can perform. So that is memory read operation or memory write, input device read or output device write. So to perform these four initiated operations, the processor has to identify the peripheral with its address. Then after identifying the peripheral with which it has to communicate, then the processor transfers the data either from processor to peripheral or peripheral to processor. Then the necessary synchronizing signals to synchronize the speed of the processor and that of the peripheral are also be generated by the processor, and the timing is also maintained by it. To perform all these operations, that is to identify the device with its address, data transfer or generation of control signals, for all these things it requires, the microprocessor requires three types of buses. They are address bus, data bus and control bus. So what is bus? Bus is nothing but a group of conducting wires used to carry information, specifically digital information. Let us see about all these buses with respect to 8085 processor. 8085 address bus consists of 16 lines, that is address bus length is 16 lines. It is unidirectional. This is because the processor generates address to locate the peripheral with which it has to communicate. So that's why it is unidirectional. The address will be sent by the processor to the peripheral. In general, 8085 has 16 address lines. Among them, 8 address lines are exclusively meant for sending higher order 8 bits of the address, whereas the lower order address byte is sent over a multiplexed address bus, which is AD7 to AD0, indicated as AD7 to AD0. This is why it is so is here the same 8 lines are going to be used for sending lower order address byte as well as for data at later time. So how these address lines and data lines are going to be demultiplexed, we can see later. And the size of address bus of any processor will decides the maximum size of the memory that the processor can access. Now let us see, if a microprocessor has a single address line, then it can identify only 2 address locations. How it is, we can see now. So let us see here, the 8085 processor has a single address line over this single address line, it can send a single bit which corresponds to an address. So with this single bit of address, so by sending 0 address, it can identify one location. So by sending 1 as an address, it can identify second location. So with one address line, it can locate 2 locations, that is 2 power 1 is equal to 2. If the processor has 2 address lines, as in this case, so the address can have 2 bits. By sending 0 0 as address, it can identify first location with 0 1, second location with 1 0, third location, and with 1 1 as address, it can locate fourth address location. So with 2 address lines, the processor can identify maximum of 4 memory locations, that is 2 power 2, which equals to 4. In the similar lines, 8085, which has 16 address lines, can locate 2 power 16, that is equal to 65,536 locations. As 2 power 10 is equal to 1024, which can be considered equivalent to 1000, that is equal to 1K. So 2 power 60 is considered to be 64 kilo locations. So that is 64 into 1024, which is equivalent to 64 kilo location. So the memory, the maximum memory that 8085 can access is 64 kilo locations or kilobytes of memory. Now let us see about the data bus of 8085. Data bus here is an 8-line bus. It consists of 8 lines for data transfer, that is 8 bits of data can be transferred at a time. It is bidirectional. The data can be sent by the processor to the peripheral, or it can receive data from the peripheral. So it is a bidirectional bus. Here we already discussed that the same lines which are utilized for sending of lower order address byte are also used for sending of data at later time, that is multiplexed address bar data bus, which is AD7 to AD0 is going to be used as data bus. Here the address latch enabled signal which can demultiplex the multiplexed address bus. When this address latch enabled signal stays high, then the information over this multiplexed bus corresponds to address. If this address latch enabled signal goes low, then the information over multiplexed bus corresponds to data. So with the help of address latch enabled signal, the address, lower order address as well as data of the multiplexed bus can be demultiplexed. For any microprocessor, the word length of the processor is decided by the length of the data bus. So if data bus has 8 lines, then it is treated as 8-bit processor. If it has 16 lines data bus, then it is to be treated as 16-bit processor, and so on. So here 8085 is an 8-bit processor because it has 8-line data bus. Now we can see about control bus. So far we have seen address bus and data bus, which are consisting of number of lines and utilized as a group. But here in a control bus, it doesn't consist of a group of lines, but it consists of different single lines used for generation of independent control signals. Here these control lines or control bus is going to be used for generation and for sending of synchronization signals. Specific control signals for each machine operation can be provided by the processor. For example, memory read, memory write, input output read or input output write control signals can be sent by the processor over these control signals. So we can say that the control bus consisting of independent lines which are used for generation or for sending of independent control signals from processor to the peripherals. So let us see the bus structure of 8085. Here we can see this is the bus structure. 8085 consists of 16 address lines. This is the address bus. Already we stated that address bus is unidirectional, that we can see here. This is from processor to either real world or to the memory or input device or output device. It can locate by sending an address. Let us see here, it can generate an address to locate memory, or it can send an address to locate input device or an output device or any other peripheral with that of the real world. Next, data bus. Data bus is a bidirectional bus. So here it can send data to the external world or to a memory or to an output device, and it can take from data from the external world or from an input device or from the memory. So data bus is bidirectional. The data transfer may take place from processor to peripheral or from peripheral to processor, whereas it can generate control signals and can send to any of the peripherals according to the requirement of the machine operation. So that is about the bus structure of 8085. Now we are going to let us see how a memory read operation can be made by 8085 processor with an illustrative example. Let us see here, we are having the processor 8085 and this is a memory chip. So first thing is, it has to identify the memory location from which the data has to be read. Here we have taken memory read operation as an example. So how data can be accessed from a memory location? This is first, it will send a 16-bit address over this address bus to the memory chip. After sending the 16-bit address, the memory decoder will decode this address and it locates the memory location with which it has to be communicate. Simultaneously, the processor can send a memory read signal over this control line. So after receiving this control signal, the particular memory location which has been previously activated will place the data and the actual data transfer takes place. This is how memory read operation takes place within a processor. Now let us see the internal data operations. So far we have seen microprocessor initiated operations. The second group of operations which the processor can perform in a microcomputer or internal data operations. So the internal data operations, first thing is, it can store 8-bit data, or it perform arithmetic and logical operations, test for conditions, sequence the execution of instructions, store data temporarily during execution of the program in read-write memory called stack. So these are the internal data operations. First thing is, for data manipulation, actually the 8-bit data has to be stored internally. So that it stores this 8-bit data in some resistors which are available internally to the processor. Over this data, according to the instruction, it performs some data manipulation operation which may be arithmetic or logical operation with the help of arithmetic logic unit consists of logical circuits or arithmetic circuits that performs these operations. Once arithmetic logic operation has been completed, then the status of the result can be tested with the help of, or can be explained or can be available to the user by means of another resistor which is known as flag resistor. That is, it tests for conditions and can made it accessible to the user with the help of a resistor known as flag resistor. This is sequence of the execution of instructions. When the processor is performing or executing a program, it reads one instruction at a time and completes the execution of that instruction. Later it goes to read for the next instruction. So when it is executing an instruction, the next instruction that is to be read and to be executed will be indicated by a resistor known as program counter. So for this sequence of the instruction execution, one more resistor is available within the processor. Then lastly, it can store data temporarily during execution of the program in read-write memory called stack. So while it is executing a program, suppose the available internal registers are exhausted, then it may need some more data for processing. Then in such a case, some of the data can be stored temporarily in a part of read-write memory which is predefined by the programmer as a stack. So the programmer will predefine which part of the read-write memory he is going to use as a stack whenever it requires. So the starting address of that read-write memory where from he wants to use it as stack has been stored in another register which is known as stack register. So now we can see about the internal data operations, what it requires. That is, it requires registers. Already we have seen for data storage it requires registers, and for arithmetic and logical operations to perform it requires arithmetical logical unit, and to have data transfer within the registers or within the arithmetical logical unit to the registers, it requires internal buses. So this shows the register array. 8085 consists of a number of registers which are available internally for it. The first one is accumulator, which is an 8-bit register. Then flag register, which is also an 8-bit register. Here B is 8-bit register and C is another 8-bit register, whereas these two registers can be grouped into a single register so as to store or so as to have 16-bit data processing. In a similar way, D can be used as an 8-bit register, E register can also be used as an independent 8-bit register, or they can be grouped into a pair, DE pair, which can be treated as a 16-bit register and can be used for 16-bit data manipulation. Similarly, H register, L register, these two are once again 8-bit registers which can be used individually or they can be grouped and can be used for 16-bit operations. Next one is stack pointer. This we have already learned about it. Stack pointer, that is the starting address of the stack which is defined by the programmer, that has been used by him as a read-write memory to store data temporarily while executing the program. So that starting address is going to be stored in this 16-bit register, because address is a 16-bit length, address has 16-bit length, so it is 16-bit register. Next one is program counter. This program counter indicates the address of the next instruction that is to be read and to be executed by the processor while the processor is executing one instruction. So within this register array, these B, C, D, E, H, L registers are called as general purpose registers. They can be used just for storage of data, whereas the leftover registers are known as special purpose registers. Accumulator, flag registers, stack pointer and program counter are named as special purpose registers because they have some special purpose. Here accumulator can be treated as general purpose register or can also be considered as special purpose register. Why it is special purpose register is because the accumulator contains one of the data while arithmetic or logical operations are going on. So one of the data must be in accumulator when actual data manipulation takes place. That's why accumulator is considered as a special purpose register. Now let us see about flag register, how the flag register can indicate the status of the result. Here actually we are calling it as flag register, but it is not actually a register. It consists of independent flip-flops. Here 5 flip-flops are going to be used to indicate the status of result after arithmetic or logical operation has been performed over the data. So they are sign flag, zero flag, auxiliary carry flag, parity flag and carry flag. Let us see about these flags. Sign flag. Once arithmetic or logical operation has been performed over the data, for example, if the result, within the result, if D7 bit is 1, then the sign flag is going to be set. So here this sign flag is going to be used in sign magnitude data representation. In general, we know that in sign magnitude data representation, the 7th bit or the most significant bit within the 8-bit data, for example, if you take the most significant bit, that is D7 bit, is going to be used to represent the sign of the data. If it is 1, it indicates it is negative number. If the most significant bit is 0, then it represents it is a positive number. So if the result has the most significant bit as 1, then the sign flag will be set. It indicates it is negative number. Otherwise, that is if D7 bit is 0, then it indicates it is a positive number, and it will be indicated by the sign flag by resetting it. That is about the sign flag. Then let us see about zero flag. Here the zero flag indicates after arithmetic or logical operation the result available is 0 or not. For example, if you take 2 8-bit subtraction, then if after subtraction if the difference is 0, then the 0 flag is going to be set, otherwise it is going to be reset. That is, after arithmetic and logical operation completed, if the result is 0, then 0 flag is set. If the result is not 0, then the flag is going to be reset. Let us see about auxiliary carry flag. Actually, this auxiliary carry flag is going to be used in BCD operations, that is binary coded decimal operations. This auxiliary carry is nothing but a carry generated from D3 bit to D4 bit when an arithmetic or logical operation has been completed. So if there is any carry that has been carried from D3 bit to D4 bit, then the auxiliary carry will set, otherwise it will reset. It is by using this auxiliary carry flag, the programmer cannot change the program sequence, whereas all other flags can be used to test the program sequence and can be made to change by using the leftover 4 flags, but auxiliary carry flag cannot be used to change the program sequence. Next one is parity flag. This parity flag indicates how many ones are available within the result, that is they are even or odd number of ones are available within the result. If after arithmetic logical operation, if the result has an even number of ones, then the parity flag is going to be set. If the result has odd number of ones, the parity flag is going to be reset. So that is about the parity flag. Let us go for carry flag. Carry flag consists of the carry flag is set if the arithmetic or logical operation results a carry from D7 bit. That is, if you take two 8-bit numbers and if you try to add them, for example, if the sum result in 9 bits, that is there is a carry. So instead of 8 bits, we are going to have 9 bits. This carry generation is indicated by this burn. So carry flag will be set if there is a carry, or it will be reset if there is no carry after arithmetic and logical operation. So that is about the resistor array within the 8085. Now the third group of operations that the processor can perform within a microcomputer are externally or peripherally initiated operations. Here, so far we have seen internal microprocessor initiated operations and internal data operations. That is what the processor can perform to communicate with a peripheral, There is a processor initiated operations, and second one is data manipulation operations. That is within the processor how the data is going to be transferred, stored or transferred. So third group of operations are peripheral or externally initiated operations. So by these operations the processor can be made to activate by means of some external signals provided by peripherals. So let us see these externally initiated operations. First one is reset. Here the special pins are provided over the processor to provide these external signals by means of peripherals. Here a reset signal, which is active high signal sent by a peripheral, can make the processor to suspend all its internal operations. That is, the processor will resets its program execution, thereby the program counter will resets to 0000 address. That means the program execution will start from this 0000 memory address location. This is how an external device can make the processor to stop all its internal operations and to start its execution from this starting address, that is the initial address 000 of the memory location. Second signal by which the peripheral can make the processor to interrupt is an interrupt signal. Here by sending an active high signal over this interrupt pin, the normal execution of the program of the processor can be interrupted, and it can be asked to perform to execute some other program which may be required immediately. So the processor can be interrupted from its normal execution of the program and can be made to perform some other program execution which is called as service routine. So that is about the interrupt signal. There are two more signals which are ready signal and another one is hold signal. Here a ready signal is used to synchronize the speed of a slower peripheral with that of the processor. If an active low signal is sent over this ready pin, then the processor will enter into wait state. So an active low signal over this pin which is sent by the peripheral will indicate the processor that the peripheral is not ready to communicate with the processor. Then the processor can accept this ready active low signal and can kept in wait state, or it may remain in its wait state without doing anything. When it receives active high signal over this ready pin, then only the processor will be further performs its operation. That indicates that the peripheral is now ready to communicate with this processor. So in this way the ready signal can be used to synchronize slower peripherals with the microprocessor. For example, if you take an analog to digital converter which is an input device, it has to convert analog data and has to supply the digital data to the processor as an input data. The processor is a faster device, that its speed of operation is very fast compared to with that of the A to D converter. In such a case, analog to digital converter may take some time to convert the analog data to digital form. So meanwhile the processor is very anxious to read the data. In such a case the processor is held in wait state by sending an active low signal by the analog to digital converter. Only after its completion of conversion, then it will send an active high signal over this ready pin, and then the processor will now reads the data from A to D converter. In this way, ready pin is very much helpful to synchronize the slower peripherals with that of the microprocessor. The last signal is hold signal. Sometimes some peripherals may be interested to use the buses of microprocessors. In such a case, they will send an active high signal over this hold pin and ask the processor to relinquish its control over the processor. So, when it receives this hold signal, then by accepting that signal, microprocessor leaves its control over address and data buses and allows the external peripheral to use them. So, that is about the externally initiated operations. Now, let us see the pin diagram of 8085 microprocessor. 8085 is a 40 pin IC which is available in dual in line package. So, now let us see, here it is a 40 pin IC, okay, 1 to 20 and 21 to 40 pins. Now, here X1, X2, these two pins are provided for connecting an external clock which is a crystal. Generally 6 MHz clock is going to be connected to these pins, because internally divided by 2 counter will be there, which divides this 6 MHz clock and provides 3 MHz frequency to 8085. So, 8085 is a 3 MHz chip, or its frequency is 3 MHz. Let us see serial data pins. So far we use these data lines, the 8 lines for parallel data transfer, that is all 8 bits can be processed or can be accessed by the processor at a time. Whereas in case of serial data transfer mode, the data has to be sent one bit by another on a single line. So here SID is serial input data pin, over which in serial data transfer the data can be inputted to the processor over the serial in data line, whereas SOD is serial out data line, over which the processor can write data into the peripheral device. Next one is interrupt pins. So previously we have seen what is an interrupt, that is any peripheral can be made to interrupt the processor regular execution and can be asked to perform some other important program which is called as service routine. Here these are the 4 pins that are available to provide interrupt signals to the processor externally. They are trap, RST 7.5, 6.5, 5.5 and interrupt request. So among these 5 interrupts, trap has the highest priority, the next priority goes to 7.5, 6.5, 5.5 and interrupt request respectively. So here interrupt acknowledge, which is outputting pin, that is when it receives interrupt request, then if it accepts that interrupt, then it will indicate to the peripheral or it can acknowledge its acceptance by sending an active low signal over this interrupt acknowledge pin, which is outgoing pin. Then these are the 8 lines which are used for sending of address as well as for data transfer, which is multiplexed address bar data bus. Here these 8 lines are exclusively used for sending of higher order address byte. So this is address latch enable pin, which is used to demultiplex the multiplexed address bar data bus. So now S1 and S0, these two are status pins, and IO bar, M bar, read bar, write bar, these are control signals. By using all these 5, the different machine operations, for different machine operations control signals can be generated, which we can see later. Then reset in, previously we have seen the externally initiated one of the provision is resetting the 8085, which is reset in. A peripheral can reset the 8085, whereas this is reset out. The processor can also reset any other peripheral by sending an active high signal over this pin, which is outgoing pin. Then hold and hold acknowledge ready bar, that is already discussed. So a peripheral can send a hold signal which can be made the processor to relinquish its control, whereas hold acknowledge can be an acknowledged signal that it is ready to leave its control over the bus. And so this is how the status signals and control signals are going to be generated, that is IO bar, M bar, S1, S0. Here IO, if it is active high signal is there, IO bar M bar line, then it corresponds to input operation. If there is low signal over this pin, it corresponds to memory operation. So these three corresponds to memory operation, these two corresponds to input output operation. S1, 1, S0, 0 corresponds to read operation. So these two are read operations. 0, 1 stands for write operation, these two are write. Here this is memory read and this is opcode fetch. To discriminate between whether it is data read from the memory or instruction opcode is going to be read from the memory, here S1, S0 will be 1, 1. So finally we are going to see the architecture of 8085. So that's we are going to see here the architecture. Here it is basically consists of arithmetic logic unit and that of instruction decoder, resistor array, accumulator, flag resistor, temporary resistor, then timing and control unit, serial input output block, interrupt control, and these are the this is about the architecture of 8085, which we have seen already about already studied about the general purpose resistors and that of the flag resistor, arithmetic logic unit, and how the bus structure of 8085 is available, the pin diagram of 8085 and the function of each pin we have seen. With the help of IO bar, M bar, read bar, write bar, these three control signals can be used to generate the four control signals: memory read bar, memory write bar, input output read bar and input output write bar, by using negative NANDs that we can see in the next class with the help of another author. Okay, thank you one and all.